Oh, it's counting down. It's counting down.
Yeah, I just have to press go live, and then that should popping up soon. Okay, why is it live in 5 minutes?
It's set up at 6 p.m. It's counting.
Right.
Down.
Oh, okay, I think we have live one now. We have the live feed on YouTube. Can you see that?
Yep.
Okay.
It says that.
Great. Okay, I try to turn off the sound before she's feeding back in the loop.
Yeah, I think that's a 20 seconds delay or something.
Yeah, there's some delay to it. Great. Yeah, no, that's something like 20 seconds delay. Yeah, I think that's what this usually is. So if you look in the Zoom and YouTube at the same time, you might see that on the YouTube is something like 20 seconds delay. So I think we just pay our attention on the Zoom and not worrying too much with the YouTube live. Otherwise, you will be a bit experiencing something like a very strange, right? Okay, so right, shall we kind of like getting things started?
Maybe we can wait a few more minutes to
sure.
make sure.
Yeah. Okay, in that case, let me see. I will make you a co-host. Yeah. So I do make me a co-host just in case I drop out or anything like that. Okay, so now you made into co-host. Okay, so in that case, I'll transfer the floor to you, Manine. So so you could give introduction.
Yeah, I am a co-host now. So do we need to record this one if it's go live on channel, or we record anyway?
I think usually, yeah, you get that on YouTube, but yeah, I'll press a record button anyway, so I will do that. Okay.
We can wait a little bit to.
Right, sure.
Fill up the audience more.
Okay. Not sure if we can see how many people on the live stream on YouTube. Can we tell? Probably not, unless they say something, right?
It seems like I'm still unable to share the screen. So.
Ah, okay. Hang on.
I do it. Sorry, I forgot.
That's fine. There is option ask to share, I think. Ask to share video. If you click on his name.
I cannot find the button, but I can. Can you share the screen again, Warit?
No, I still can't. It says host disabled it. So maybe Uten, can you also make Warit co-host also? That will fix the problem.
Oh yeah, good idea. So I make Warit also into a co-host. Okay, can you try?
Okay, yeah, I can do it now. Yes.
Great.
Thank you.
All right, if you just log in, we are now about to start the live session on the talk, the public talk during the TCAP workshop. So we're just waiting to pick up a few more people to join the live sessions.
It's not even 6 o'clock yet, actually.
It's not? Really?
No, it's not. It's 5:59.
Oh, okay. That's strange because actually on the computer I'm logging into, it said 6:05 already, so that must be 5 minutes earlier. Right, okay.
So we are quite on time.
I was worried a little bit that we were actually not making a good time and might be late. Okay, fine. I was a bit nervous, isn't it? Okay, so whenever you're ready, so Manine, okay, you can start. I will mute myself and turn on my camera now. I mute before I actually finish my sentence.
Okay.
Okay.
I think we can wait for maybe a few minutes, or what do you think?
Sure, I leave that up to you. Okay, but whenever you start, I will press the record. So when you will start, just let us know. Okay, I leave that up to you now.
Okay, thank you. Maybe. Okay, I think we have some quite number of audience now. I think we can start. Okay. 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 Hi everyone. Welcome to the public talk of the second Thai CTA workshop. My name is Manine Vechagama. I will be the chairperson for this session. So during these 2 weeks, we are having an online workshop called the second Thai CTA workshop, which is about astroparticle physics, gamma ray research. There are several sessions, including lecture, tutorials, and also public talk. The workshop is organized by Thai CTA members and supported by National Astronomical Research Institute of Thailand, or we call as NARIT, Durham University, Kasetsart University, Khon University, Sri Nakarintara Virod University in Thailand, Newton Fund, and also ICTA. During this workshop, there are 2 public talks, and this is the first one. These talks go live in NARIT YouTube channel. I should tell you that. So if you have any question, you are welcome to ask during the talk or leave the message in the chat, or you can keep the question and ask them at the end of the talk. So next, I would like to thank Dr. Warit Mitthumsiri for accepting the invitation for giving the talk today. And let me give a short introduction about him. So Warit got his PhD in physics in 2013. During his PhD, he worked with Stefan Funk at Stanford University in USA with the thesis title Local Cosmic Ray Measurements with Fermi Large Area Telescope. After that, he came back to Thailand and worked at the Department of Physics, Mahidol University in Bangkok since 2014. He is also a member of the Fermi collaboration. So today he will give a talk about research on high energy gamma ray with the Fermi Large Area Telescope in Thailand. So let's welcome Warit Mitthumsiri. Okay.
All right. Thank you for inviting me to give a talk today. So let me share my screen. Okay, so today I would like to tell you something about the research on high energy gamma ray with Fermi Lab that we do in Thailand. By we, I mean there are a number of people, including a lot of students at the space physics group at the Faculty of Science, Mahidol University. So the Fermi Gamma Ray Telescope.
Sorry, Warit, could you please go full screen? Then we can see your slide better.
I thought I already went full screen. How do I do that? Should I share?
To view, you can go to view. Sorry, in your PDF, there is the view option and you can select full screen. I think. Yeah,
Does this work?
Oh, yeah, this works better. Thank you very much.
All right, thank you. Sorry about that.
No problem.
So I just want to mention quickly that the instrument, the Fermi Gamma Ray Space Telescope, is mostly funded by NASA, the US, and a few other countries like Japan, Italy, and France. Okay, so here is the picture of the Fermi Lab before launch. So it was put in this rocket and then launch it up to orbit the Earth at the altitude of about 560 kilometers. So, so I'm wondering, do you see the cursor, the mouse that I'm pointing on the screen? Ajahn Maninet, are you able to see like the mouse? We can see it.
Yes, okay. Yes. Yeah, we can see.
Okay. So this is the how the Fermi Lab looks like. So the main instrument on the Fermi Gamma Ray Space Telescope is the Large Area Telescope, or the LAT, which is this kind of yellowish thing here. So the spacecraft is launched in 2008, and it's orbiting the Earth at about 560 kilometers, and it completes one orbit in 1.5 hours, but it would survey the northern sky for one orbit and then survey the southern sky for the next orbit. So it it observes the entire sky every 3 hours. So the LAT is a gamma ray detector, and it works by converting the gamma ray photon into a pair of electron and positron. So when a gamma ray comes in, it strikes with the what's so-called the conversion foil, and then it converts into an electron-positron pair, and then the tracker system here would record the direction of the electron-positron pair so that we can reconstruct the direction of the original gamma ray. And then the calorimeter at the bottom of the LAT would then measure the energy of
of the gamma ray. So the size of the LAT is about 3 square meter as a cross-section area. And its resolution is very good compared to previous instruments. So here is an example of the Gammaray Sky that Fermi LAT has observed. So this blue map here is like the entire sky, but unwrapped it and then put it flat here so that you can see the entire sky and see what objects are shining in gamma rays. So you can see this bright bright stripe in the middle. That's the galactic plane. So the reason why it's bright in gamma ray is just because there are a lot of dust and medium along the plane. So when the high energy particles, the cosmic rays, interact with these dust and gas, then they can emit gamma ray. So, and you can see some dots, like some point sources spreading around too. Most of the dots that are circled here are pulsars. So there are some famous ones that maybe it's a good thing that we recognize is, for example, the Vela pulsar is like one of the bright pulsar, gamma ray pulsar in the sky. So you can see how bright it is. And if you look at it from other wavelengths and then try to make a beautiful photo of it and zoom in, it would look something like this. But here you need a combination of many wavelengths. So if you just observe it in gamma ray, you cannot see it in this much detail. And here's the Crab Nebula. It's also the famous supernova remnant with a pulsar in the middle. So it's right here. This is Gaminga. So its name is a little strange, right? I think it's because it's a gamma ray source inside the Gemini constellation. So this gaming here is from Gemini and GA is from the word gamma ray. So it's like one of the first gamma ray sources detected by human. There are some other objects, right? Like these small point source here that is far from the galactic plane. These are mostly like active galactic nuclei. So like at the center of massive galaxies far, far away, there can be some, there exists some supermassive black hole, which can emit very high energy particles, including gamma rays. And as I said earlier, this diffuse emission from the galactic plane is just mostly from particles interacting with gas and dust and then emit gamma ray. So this is just the overview of what Fermi can see. And then I would like to tell you about what we do here in Thailand. And the major topic that we study is mostly looking down at the Earth. Like most people in the collaboration, they would look up in the sky and see the like exotic objects in the universe. But we would like to do something different. So we look down and look at our Earth. And the Earth is actually a very bright gamma ray source. So why is it very bright? Maybe first I have to introduce you what cosmic rays are. So cosmic rays are energetic particles in space. So if you go out to like far, far away from the Earth, then there are a lot of high energy particles like bombarding your body like all the time. And most of those particles are protons and a small fraction of other particles, including gamma rays. So if you look at this plot here. So the x-axis is the energy and the y-axis is basically flux. And here, the top line here is the flux of cosmic ray proton. And the open circles and the open squares here are the astrophysical gamma rays. So you can see that the flux of proton is much more is much higher than the flux of gamma rays. So actually, like astrophysical gamma rays are just a small component in the cosmic ray. But the solid square here, this is the gamma ray emitted by the Earth, and you can see that it's much brighter than the gamma ray from the sky. It's just because that the Earth is much closer to the detector, which is the lab. So that's why the Earth is very bright in gamma ray. And we will talk about how the Earth emits gamma ray in the next slide. So just this slide, I want to introduce you a little bit about cosmic rays. So where do cosmic rays come from? There are many sources that produce cosmic rays. Most notably, like within our galaxy, probably the majority, like the main producer is the supernova. And from extragalactic source, there could be some active galactic nuclei. Pulsars, stellar winds also contribute a little bit. The sun also contributes to a small portion of low energy cosmic rays, but at above, say, 10 GeV or so, then the sun does not contribute that much. Most of the cosmic ray above 10 GeV here are from other things. So what is interesting about cosmic rays? It's the interstellar matter that travel to us, and it's probably the only accessible interstellar matter that we can study. So it's good that they come to us so we can see what the universe is composed of. And for a more practical purposes, like if we want to do a longer space travel, then cosmic rays would be something we have to take into account. Like we cannot stay in space for too long because it would be harmful. Like these high energy particles would be harmful to us, both to like living things and also to the electronics. So if we know more about it, then we can plan better for a longer space travel. So here, this is how the Earth produces gamma ray. Basically, when cosmic rays strike the upper atmosphere, so most of the Earth atmosphere is nitrogen molecules, right? So basically, like cosmic ray proton would strike with the nitrogen molecules, and then it creates shower of secondary particles. And some of those secondary particles can decay into gamma rays, and these gamma rays are detected by the Fermi Lab. So if you imagine, like if you sit on the lab and suppose your eyes can see gamma ray. So if you sit on the lab and look at the Earth, this is what the Earth would look like if you can see the gamma ray above 10 GeV or so. So the Earth, the solid Earth, is at the center, and you would see bright gamma ray rings, a bright gamma ray ring around the Earth. So why does the Earth look like a ring like that? It's just because, as you know, the gamma rays are produced from cosmic rays striking with the atmosphere, and for high energy cosmic ray and high energy gamma ray like this, then the interaction would occur pretty much along the forward direction. I mean, cosmic ray comes in from behind the Earth, and then it grazes through the upper atmosphere, and then it forward scatter gamma rays into the detector. So basically, like the gamma rays travel the gamma ray is traveling along the same line as the cosmic ray. So if the cosmic ray like arise from behind the Earth, then of course that we cannot see the gamma ray as a result, because the physical Earth itself would then block that gamma ray, right? But if the cosmic ray arise at too high, too far from the Earth, then there is not much air for it to interact with. So there's not much gamma ray produced. So there must be some optimal range that the cosmic ray is arriving and producing some considerable amount of gamma ray to be detected. And that's why we see the ring here. Like if the cosmic rays graze through the too far from the Earth, then we cannot really see anything. But the center of the Earth here, like the Earth itself is blocking the gamma ray from behind it. So what we can see is just the result of cosmic ray particle grazing through the upper atmosphere of the Earth.
Sorry, I would like to, there was a question from the audience that asked about how about oxygen?
Oh yeah,
cosmic ray too.
Nitrogen probably are not that different in the eyes of cosmic ray proton, right? It's just one atom with 7 protons and one atom with 8 protons. So they're pretty much the same for cosmic ray proton. They just strike those molecules and create gamma rays in pretty much the same way.
Okay, basically every molecule there.
Yes, yeah, basically every. So it would break down to just proton and neutron. Right? Nitrogen is just 7 proton and 7 neutron. Oxygen is just 8 proton and 8 neutron. So basically it's the collision between proton and proton. That's what it comes down to. Okay.
Yes, okay, please continue. Sorry.
All right, sure. So this is the spectrum of the Earth's gamma ray. So the x-axis is energy and the y-axis is the flux. And we can just care about these open circles here. That's the flux as a function of energy from the Earth limb. And this this spectrum is well described by a power law. So by a power law, I mean the functional form of this line can be described by a function of like 1 over e to the some number, and this number here is called the spectral index. This 2.8 here. So this is a power law, and when we plot it so when the x-axis is in the log scale and y is in the log scale, this power law looks like a straight line in this log plot, and the slope here is minus 2.8. So this number 2.8 here is called the spectral index, which might be which I will refer to a few more times later in the talk. So since we can measure the spectrum of the Earth's gamma ray, and we know we can model the cosmic ray air interaction, we have a way to backtrack the cosmic ray proton spectrum. And what's interesting is that in around 2011, there's a report from the satellite mission called Pamela, and they report that there's an abrupt change in the shape of proton spectrum at around 250 GeV or so. So if you look at the spectrum of cosmic rays in a very wide energy range, so here, and this energy range is extremely wide, and you can see that the spectrum of cosmic ray is well described by a power law, but there are some abrupt change in the slope, and these features are known as the knee. About 10 years ago, there would be 2 features that are known, which is the knee and the ankle. So there's some change in the slope here and here. But more recently, another feature has been detected, which is called the second knee. So there's some change of the slope right here. And in 2011, there's some report that another feature might exist here at this quite low energy. And what is interesting about these features is that they would provide us some hint about the origin of cosmic ray and the cosmic ray propagation in the galaxy. So if we know all the features and we try to put it in a model, then we can have a better understanding of how cosmic rays are created and travel and propagate in the galaxy. So one interesting thing is that when Pamela report this feature, the energy range here, which is about 250 GeV for proton, is within the range of the gamma ray that the LAT can observe. So it would be interesting to use the Earth gamma ray spectrum to backtrack and see if we also confirm this feature. Okay, so this slide is a little technical, but I just want to tell you a little bit about the idea of how we would indirectly measure the cosmic ray proton. So basically, we can model a cosmic ray spectrum with a simple model, like a single power law model or a broken power law model. So a single power law model is just there are just two parameters, which is the normalization and the spectral index. But a broken power law model would now have the break energy, and also there are two spectral indexes, so that it can create this kind of change in the slope in the spectrum. So by having these models, and we can vary the parameters like the normalization and the index, and then we pass it through the proton air interaction model producing gamma ray, and the resulting gamma ray flux, we can fit it to the Earth gamma ray spectrum, and then we can try to vary the parameter so that the model gamma ray flux is best fit with the actual measurement. And when that occurs, then we know that, okay, that's the best cosmic ray spectrum that we can infer from the Earth gamma ray spectrum. And here's the result we published in 2014. Basically, we cannot really confirm the break here that Pamela report. We cannot confirm it clearly from the Fermi Lab data alone. But the best fit model, these are the two best fit model that we can infer from the Earth's gamma ray measurement. So if we assume that the cosmic ray proton is just one single power law, this red line here is the best fit model that we got. But if we assume that the proton spectrum is a broken power law model, and this is the best model that we get, and you can see that it's quite consistent with other measurements, like these points like in gray and black here. These are direct space-based measurement from satellite or balloons. So we can, our best fit model is consistent with the direct measurement, but we cannot absolutely conclude the break from just the Fermi Lab data alone. Well, but that was in 2014, but more recently, like in 2019, there are some other space-based measurements. The famous ones are AMS-02, and this one in red here is another one called Colette. And you can see that now the two has clearly confirmed the break here at a few hundred GeV in the proton spectrum. So at this point in time, in 2019, 2020, we have confirmed another feature around this energy. in the cosmic ray spectrum, and that would be interesting for in the theoretical and modeling point of view of what produces this feature. And also, I would like to mention that we also use a larger data set, and master student, Mr. Payung Kwamdi, also tried to repeat the measurement with the Fermi Lab data with more amount of data and better technique. And this is what he got. Basically, the best fit model is also consistent with the direct measurement, but it's still at this point, this kind of indirect measurement wouldn't beat the direct cosmic ray measurements like this anymore. But it's still something good that we confirm the robustness of the analysis, and we still obtain the same result with a much larger amount of data in 2020. Okay, and another work that we have done is the analysis of the intensity of the Earth gamma ray as a function of geographical location. So here is the photo. You can call it a photo of Earth in gamma ray. There's one variable that I would like to mention is this theta nadir. So if you sit on the lab and you look down at the Earth, and suppose your eyes can see gamma ray, this is what you're going to see from the Earth. And the theta nadir here is the angle measured from the center of the Earth to whatever position that you are interested in. For example, this bright ring here of the Earth's gamma ray emission is located at theta nadir of around 68, 69 degrees. It's just because the LAT is quite close to the Earth. So the Earth is almost like covering the whole field of view of the LAT. So you can call this theta nadir, or you can use another variable that is closely related to theta nadir, which is zenith angle. Basically, it's just the inverse of theta nadir. So the theta nadir is measured from the line connecting the LAT to the center of the Earth, but theta zenith is just the angle measured from the line pointing away from the Earth. So the relationship between these two variables is just theta zenith is 180 minus theta nadir. And so if you plot the Earth gamma ray as a function of theta nadir or theta zenith, then you have this kind of peak over here, right? Because you can see that at low theta nadir, there's not much emission. As you go to higher theta nadir and go up to 68 degrees, that's the peak of the emission. And then when you go to larger and theta nadir, then the emission is gone. So this is what we are measuring. But this plot is expressed in a zenith angle. So 68 degrees in nadir is 112 in zenith angle. That's why we see the peak here. And you can see that the peak of the gamma ray, the Earth's gamma ray emission moves over time. In 2018, it's here, and in 2009, it's here. So it moves to smaller and smaller theta zenith over time. This is just because the spacecraft is falling, like the altitude of the spacecraft is decreasing over time. It's just because of the drag from the air. Right? So the Fermi LAT is actually slowly falling down to the Earth. So when it falls down to the Earth appears bigger and bigger to it over time. And that's why this bright ring here gets larger. So by getting larger, it means the peak goes to a lower theta zenith. So we can use the data from the peak to towards the Earth. So the peak towards the Earth is here to analyze and try to take a photo of the Earth in gamma ray. And what would we expect if we can take a photo of the Earth in gamma ray? Well, the Earth's gamma ray is produced from cosmic rays, right? And cosmic rays are mostly charged. So we would expect that it would be highly related to the geomagnetic field. So in this map here, this is the map of what's so-called the rigidity cutoff of the Earth. So the Earth has a magnetic field around it, right? And when charged particles want to arrive to the atmosphere, it has to penetrate through the magnetic field. So it has to have enough momentum to penetrate the magnetic field, because if it doesn't have enough momentum, then the magnetic field would just deflect these charged particles away. So the parameters that would determine if the particle can penetrate through the magnetic field is called the rigidity. So the rigidity is momentum per charge, because if a particle has large momentum, then it can penetrate through the magnetic field easily. But if it has a large charge, then it would be more difficult, because if it has a large charge, then the magnetic field can affect it more. So in this map, you can see that a particle has to have a rigidity of, say, I don't know, 15 gigavolt to arrive somewhere in Africa, for example. It has to have the rigidity of at least 11 gigavolt to arrive at South America, for example. So you can see that it's very easy for particles to arrive at near the North and the South Pole if it just has the rigidity of 1 gigavolt. It can arrive to the North and the South Pole. And what's interesting about this is that, you know, where is the hardest location that cosmic rays can arrive? So it's here. It's our home in Thailand. So charged particles has to have at least 17 gigavolt to arrive to somewhere in Southeast Asia. So actually what we are living right now is a quite special location on Earth, where it's the most difficult for cosmic rays to arrive. So here is the result of the analysis of the gamma ray intensity at different latitude and longitude location of the Earth. So there are 4 panels here: North, East, South, and West. It's just because like if you imagine you go on a satellite and you have a gamma ray camera, and you kind of like tilt your camera to the north and keep taking the photo of the Earth, this is what you're gonna get. And if you kind of like tilt your camera to the east and the south and the west, so these are the gamma ray maps that you're gonna see. And you can see the variation of the gamma ray intensity of the map here. So the bright blue color means the gamma ray is brighter, and the dark blue is when the gamma ray is dimmer. And you can see that it's quite dim around Thailand, right? So as I just said from the previous slide, this is where it is hardest for cosmic rays to arrive. So when it's hardest to arrive, then not much cosmic rays can arrive here and strike with the air, and that produce field gamma rays, and that's why we have a dim intensity here. While if you go to the somewhere near the North or the South Pole, right here where the rigidity cutoff is low, then you would see brighter gamma ray emission. So I want to emphasize that these are the first, somewhat the first photo of the Earth in gamma ray that humans have ever taken. I mean, in geographical coordinate. We have taken the photo of the Earth before in this kind of coordinate system, like in the kind of like Earth center, like you put the Earth at the center and you take a photo, you get this kind of thing. But never before that we have seen the distribution or the map of the gamma ray intensity for different latitude and longitude of the Earth. Okay, so and this work has been published by a PhD student in our group. And here is the spectrum of the Earth gamma ray. You can just ignore the red and the blue dots here. They are just to compare with previous work and to show that, okay, our work is consistent with previous work. So you can just care about the black and the blue plots here. So the triangles here are the spectrum from the west. The triangle pointing up is from the west. The triangle pointing down is from the east. And the other symbols are from the north and the south. So we can see that the Earth gamma ray from the west is the most intense, and the gamma ray from the east is the least intense. That's just the effect of the magnetic field that we all expected. But what's interesting is that we can see how the effect is decreasing at higher and higher energy, and this gives us some information about at the maximum energy that the Earth's magnetic field would affect cosmic rays. And also the bottom panel here is also interesting. This is the ratio of the Earth's gamma ray intensity for two different periods. So for the I min here, that's the intensity during the solar minimum, and I max is during the solar maximum. So the sun goes through like a cycle, solar cycle every 11 or 12 years. So the sun would like have a lot of sunspots and very active for a certain year, and then the activity would then decrease, and the activity would then go back to the active level again after 11 or 12 years. So we measure the Earth's gamma ray intensity during the minimum activity of the sun and during the maximum activity of the sun. And then we can see that during the minimum activity of the sun, the Earth's gamma ray is brighter than the when the sun is active. And that's might be a little counterintuitive, right? But actually that makes sense. It's just because when the sun is active, then we have strong solar wind and magnetic field that kind of like push out cosmic rays. So when the sun is active, the cosmic rays push out, so the Earth's gamma ray is dimmer. And when the sun is not as active, it's not very strong against cosmic rays from other parts of the galaxy. So more cosmic rays can hit the Earth, and then the Earth's gamma ray is getting bright. So that's why we see that the intensity during the solar minimum is higher than the solar maximum. But this effect decreases with energy, because at the end, like when we talk about very high energy cosmic rays, the cosmic rays doesn't care about the sun anymore. It doesn't care if the sun is active or inactive. The cosmic ray has high enough energy to penetrate through anything. So this kind of effect decreases with energy. And another possible effect that we are planning to take a look is the breathing of the Earth's atmosphere. The hypothesis is that when the sun goes through the solar cycle, like being active or inactive every 11 or 12 years, then the amount of radiation shining to the Earth would then also go through a cycle, right? And hypothetically, like if the sun is more active, there could be more ultraviolet or solar wind from the sun that would heat up the Earth's atmosphere, and maybe the atmosphere would then expand more when the sun is active. Or when the sun is less active, then the atmosphere would then kind of like shrink, the thickness becomes smaller. So maybe this effect is hypothetically called the breathing of the Earth's atmosphere. It's not clearly confirmed yet. It's still kind of like a hypothesis. But we can see the possibility that if we observe the Earth's gamma ray and extract the thickness of the atmosphere, we can, use the lab data to extract the thickness of the atmosphere. Maybe we can confirm or deny this hypothesis. We have performed a little bit of the analysis, but the results are not ready to be shown yet. So we just have to wait a little longer. All right, so let's go to the next topic that we did, which is dark matter search. Well, what is dark matter? Dark matter is hypothetical matter that interacts very weakly with other matters, mostly just through gravity. But many evidence shows that most of the matter in the universe is dark matter. I mean, if you look at normal matter here, it's just about a few percent of the composition of the universe, while dark matter is like 5-6 times more abundant than normal matter. So one hypothesis, but like people cannot like, there's some evidence that dark matter exists, but there's not much else other than that. So there's one hypothesis that if dark matter particles can annihilate or decay, they might decay into 2 gamma rays. Why 2 gamma rays? Maybe for students, if you take some particle physics course, you would probably know the reason. So there's a hypothesis that dark matter can decay into 2 photons. And if we assume that the dark matter is non-relativistic, basically it's moving very slow, and it has a certain mass, then the gamma ray emission from its decay is clearly defined by a single energy, which is like half of the mass of the dark matter particle. So this is an example of one result published in 2012 about the search for dark matter emission line. So the points with the error bar here are from the actual measurement from the lab. The green here is the model from the background, and the red is the background plus dark matter model. So the dark matter model is this blue line here. So this author claims that the emission of gamma ray from the galactic center here would be better described by the background plus this kind of like line emission from dark matter decay. So this line here corresponds to the energy of about 130 GeV. So basically, like it's consistent with dark matter particle of the mass like 260 GeV, which decays into 2 photons of around 130 GeV each, and that photon would then appear as a sharp line in the photon count spectrum here. Well, but this analysis has been rejected because we look at the Earth's gamma ray emission, and we also see this kind of bump in the Earth's gamma ray emission. So that points to the effect of the instrument. Like there could be some glitch or something in the instrument that produced this kind of bump in the around 130 GeV. So because we wouldn't expect dark matter hanging around in the Earth atmosphere, right? So if we see this kind of bump from the Earth's atmosphere, then that points to some instrumental effect. So this analysis is pretty much rejected. But still, it would be interesting after the collaboration has released the next version of the data that would get rid of that instrumental effect. And we would like to try if we can see some gamma ray line from the galactic center. So one of the master students has attempted this, and here is the count, the gamma ray count map in the galactic coordinate. So the center of the plot here is the galactic center, and each of the region here, R3, R16, and so on and so forth. These are the region of interest, which is optimize for a certain model of dark matter distribution. So we would like to take a look at these regions and see if we see some sharp gamma ray emission line out of it. So the idea to do that is to add two models together. One is the background model. So we just assume that the background photon is simply described by this kind of power law. So the normalization and the energy to a certain index. And then the dark matter model is described by somewhat the Gaussian peak, something like this. So the Gaussian peak would have some parameters such as the normalization, the width, and the line energy, which is the half of the dark matter mass. So we can add these two models together and then try to fit the data by varying these parameters and quantify the significance of how well the background alone and background plus dark matter model would fit the data better. So we focus the data at higher energy, like above 40 GeV, and we use 8 years of the data. So this is the result. The blue line here, that's the background plus dark matter, and the red line is background only model. There are three examples that we show here. This R180 is just one of the region of interest. The Earth limb is just a control region. We don't expect to see any dark matter signal from the Earth, because if we see that, that's not dark matter. That's just some glitches in the instrument. And the inverse ROI here is also somewhere that we don't expect to see dark matter emission, because the inverse ROI is the region along the galactic plane. So in this region, the emission from the gas and dust or normal astrophysical sources are very bright, and it should just clearly dominate the dark matter emission. So, and we quantify the significance of each of the lines. So we move the possible dark matter line and then fit the model to the data. And the bottom panel here shows the significance. And the criteria is that any line that shows a significant above 3 sigma would be something we would take a look at. But you can see that there's nothing above 3 sigma for any region at all. The highest significant we see here is here, but it's from the inverse ROI, which is not somewhere we expect to see dark matter anyway. And it's also still below 3 sigma. So the conclusion is that we don't see any significant lines. And yeah, we have used a lot of data already. I mean, right now we have 13 years of data, but changing from 8 to 13 years, it wouldn't add much to the statistics. So maybe the conclusion is that simple line search like this may not work. We may have to use some other complicated or sophisticated method to search for gamma ray signal from dark matter decay or annihilation. Okay, and the last topic that I would like to tell you about is a new method to search for high energy gamma ray sources. Here is the most current and official release of all the sources that Fermi Lab has detected. So far we have detected more than 5,000 sources distributed throughout the sky here. So most of the sources that the lab sees are the AGN, I believe. And also there are a lot of unknowns, like the gray sources here are mostly unknown. We don't know what they are, but we identify them as clearly as gamma ray sources. But this comprehensive source list focuses on energy from 50 MeV above. So I mean, starting from 50 MeV. So if we focus more on higher energy, like such as above 10 GeV, maybe we'll see a different population of the sources. So that's what we are aiming for. And what's also good about looking at like somewhat the higher energy of the LAT is that if you look at this plot here, which is the sensitivity of different instruments at different energies. So you can see that the Fermi LAT is a space-based instrument that has some energy range that is overlapping with the ground-based instruments. Like most of other space-based instruments are at lower energy. So if we somehow can detect some sources at the upper energy range for Fermi LAT, then those sources might also show up to other ground-based detectors such as CTA too. So the advantage of Fermi LAT is that it's orbiting around the Earth, right? So it sees the full sky. It has a good sky coverage, but its sensitivity can go up to maybe around 100 GeV. That's it. Like at higher energy range, its sensitivity decreases quite rapidly. But for ground-based detectors, it can cover high energy part with high sensitivity, but the coverage of the sky is not as great as Fermi LAT. So maybe Fermi LAT is good for surveying and trying to get the list of the sources, and the ground-based instruments might be better at like focused analysis of each source in detail. So the alternative method, we try to pick out some high energy sources of gamma rays that we scan the sky and try to look for groups of gamma ray photons. Like if you see more than 2 photons, like 3 or more photons arriving compactly, like within 1 degree and within a certain time, like we try 3 different times. So 3 or more photons within 20 minutes, 90 minutes, or 192 minutes, and within 1 degree radius, then these photons are likely, not likely, I mean, they would be interesting that if these are new gamma ray sources or they are just coincidences of unrelated gamma ray, we just happen to arrive near each other. So with this method, we can focus more at higher energy, like above 10 GeV, because to produce this kind of source catalog at lower energy, like they would have to use a different method, like use a more complicated template and modeling to pick out the sources. But they have plenty of statistics because they go to lower energy. But when we go to high energy, above 10 GeV, there's not much photons left. There are very few photons. Like at the end, they're just 850,000 photons. So this method would be more sensitive to some source that is flaring at high energy. Okay, so for this analysis, we use 10 years of data above 10 GeV and try to look for this kind of groups of photons, which we call clusters of photons. So here's the result. So these are the clusters that we found. Most of the work here has been completed by a master student, Mr. Jantaler, this year. So these are the distribution of the clusters that we found, and we can try to look for the counterparts of each of the cluster and identify what objects we are seeing. And the things that are interesting are the ones that have no counterpart, like the ones that we find, but it has never been seen by anyone else. So those are identified by these star symbols. So these are the clusters that do not associate with any other known sources. But the caveat is that the ones on the galactic plane like this, they're probably just probably some coincidental effects, like they're just unrelated photons that happen to arrive near each other. But the ones that are like at high latitude, like this, like far away from the plane, like this one, or maybe this one, that is something that is, it would be hard to explain that by coincidence. So that might be some real new sources that ground-based instruments can take a look at. Okay, so these are just to show the population of different types of sources that we find from this analysis. And here's just the summary of the analysis. On the galactic plane, we find roughly like 1,000-something clusters, and a few of them have no counterparts. But I would doubt the clusters on the galactic plane, which there could be some chance coincidences. But the ones here at high latitude, like these three, would be something interesting, because these clusters are probably likely some new sources that no one has detected before. So here's the conclusion of this talk. There are three main analyses that we have tried at Mahidol University in Thailand. So the Earth's gamma ray analysis has a lot of stuff in it. We can try to use it to reconstruct the cosmic ray spectrum, to use it to calibrate the instrument, try to see the spectral variation over time, and create the first geographical gamma ray map of the Earth. So we also try to look for dark matter line emission, but we don't see anything. And then right now we are also trying to uncover new types of new sources at high energy, which might potentially be interesting for ground-based telescope too. And hopefully there'll be more results to come in the future. So that's all. Thank you.
Thank you very much for telling us many interesting research in Thailand. I must say all of them are very interesting. We have some questions here that I can ask you. They are from the audience.
Yes, please.
Yeah, I start with the first one. So the first one is from Chakrit. I think according to the proton spectrum, maybe. Is it correct, Chakrit? Is the proton spectrum plot? Yeah. Is this one? Okay, let's see. Okay, yes. So he asked a question that what are possible explanation for the feature at 100 GeV?
Yeah, that's a good question. I cannot answer it right away, but I can speculate. Like, for example, that could be two different types of sources. Like maybe this one is pulsar. So the pulsar is creating this population of proton, and then it dies down at this energy. And then there's another different population of proton that comes in. Like, for example, I don't know, maybe supernova remnants or something else that that starts to dominate at higher energy. So that's why you see the connection between the two populations, and you see this kind of kink in the spectrum. Yeah, and that would give us some hints about how to model the cosmic ray origins.
So the model that you used and the second one, so is this based on any source, or is just a mathematical function?
Yeah, it's just mathematical function. It's very simple. It's just this. There's just two models. If you assume a single power law or a broken power law, and what you get out is just this kind of line, right? So you get one line, that's simple power law, and a broken power law is just a line with a break. Yeah, so it's mathematical. There's no physical explanation in that.
So we still have to find out the explanation.
Yeah, Yes.
Yeah. Okay. And the next question is according to the cosmic ray spectrum plot. I think the one with the knee and the ankle.
Let me see here.
So the question is from Panda. So is there any explanation on the knee or the ankle of this spectrum?
Yes, it's the same. It's probably the same answer that I just explained, but probably like the knee here would involve something different because it's the softening of the spectrum. I mean, it comes down here and then it gets softer here. It may be related to some escape of cosmic rays outside, like the cosmic rays escaping from the galaxy and create this effect. So it's probably more about the propagation than the creation. That's my guess. But the explanation for the ankle is quite clear. Most people agree that the ankle here is the connection between galactic cosmic ray and extragalactic cosmic rays. So the galactic cosmic rays would then dominate up to this point, and then it would pretty much go down because our galaxy is not big enough to create this kind of extremely high energy cosmic rays. So the galactic cosmic rays should be cut off quite rapidly, and then the extragalactic component comes and take over above the ankle. I think this is pretty non-controversial. It's the connection between galactic sources.
So do you get your answer, Panda? Okay, I guess so. So we can move on the next question. The next question is from Narwin. So he asked, why does the sensitivity of detectors significantly drop at middle energy of most detector?
Oh, this is sensitivity, right? So it's so by being lower, it means it's good. So like if you want to detect something very like low in flux, you need the sensitivity to come down so that you can be sensitive enough to detect it. Right. So this is like the primary range of Fermi Lab is the most sensitive. So if a source is just this bright 10 to the minus 12, then the Fermi Lab can detect it. But at this energy, the source has to be at least 10 to the minus 11 for Fermi to detect. Right. So the lower here means it's good. It's the most sensitive energy of that instrument.
But I think his question also means why it's create like parabola shape. Why in the middle of the range is always have good sensitivity. You know, it's always like this shape. Why it is like that?
Isn't that should be normal behavior of the detector? Like if it is designed to detect something at a few GeV, for example, Fermi Lab is designed to detect something at a few GeV. So it is optimized to best perform at this energy. And then for the lower end or the high energy end, then of course the performance drops. And that would be the same as any other instruments. Like you would pick like the primary energy that you are interested in and try to optimize that. And then of course, like any other energy would then be not as good as the energy that you want to optimize. So it's gotta be this kind of shape, the curved shape.
Okay, thank you.
Yes.
And the question is from Utain. So he asked, what are the detection significance of the cluster gamma ray photons?
That's something we are working on. That's a very good question. So right now we haven't quantified it. It's pretty difficult to quantify because like these clusters on the galactic plane would have lower significance because they are among large background, right? But this one would be quite significant. Yes, and the way to work on that is I think we have to just do the full simulation of the sky, do the full simulation, put in the known sources, and then produce a fake source and then see how significant or try to perform the analysis with no additional source and see how much fake clusters turn up or something like that. So yes, I think that is the next step that we are planning to do, and I don't have the answer for you right now yet.
Oh, thank you very much. I think Utain have got the answer, and Amil would like to comment about the previous question. Yeah, please, Amil.
Hey, if I can, I
Yes,
believe
please.
that the low energy part, for example, for Fermi, I think it's a statistics issue. So basically, the detector do not detect any photons anymore. So that's why the sensitivity goes up. And I believe it's the same for the IICTs as well. After some energy, the detector is not big enough, so you don't detect enough particles anymore. So you are not sensitive enough anymore.
Okay, that
For the highest part. The lower part, I'm not sure. It's again due to the detector, as you said, but I don't know the exact.
Yes, I agree with you. For the higher part, then it's involve limited statistics, but for lower part here, like we have plenty of statistics, right? There are more particles at lower energy than at higher energy. So I think for the lower part,
I'm sorry.
it's something about physical, like the
Right.
optimization of the detector itself, I think.
I think it's also a matter of background, how because you receive so much photons, I guess that you are maybe dominated by the background and cannot extract the sources anymore very well.
Oh yeah, that could be, yeah, that could be a good explanation too, yes. That I agree, yes.
Thank you, Amel. So I will move to the next question. We have several questions here. This question is from Ratanapong. So he asked, how do you match the source with the photon cluster? Is that what you mean? I guess. Yeah.
Yes, I see. It's just the position. We just look at any known source within a certain radius of the cluster. It's 1 degree from the cluster. Yes.
Oh, and then he asked the next one, did you cross-match the cluster position with the catalog of known objects?
Yes, we do.
Yeah.
That's how we identify the types of the object down here.
And then what is the matching radius then?
I believe it's 1 degree. Okay. That's the instrument resolution. I mean, the LAT can separate the gamma ray from the same direction within 1 degree. So I think that's about the limit of the instrument resolution.
And then you can answer Utain's question too. Then the radius of the region is around 1 degree. How do you identify the counterparts?
Yes, it's the same answer, right? So
yeah.
So we look for a counterpart within 1 degree from the detected cluster.
Yeah. And then Utain also asked, how confident are you with these association with counterparts?
Yeah. So we just look at the positional information, right? So it's hard for me to quantify that. Yes, and I'm not really sure.
And do you know what sort of object are these counterparts? That's what his next question.
Well, the types of the objects are shown here, right? So some are pulsars, some are, I think most of them are, you can look at it. Actually, most of them are unknown. I mean, it has been detected by other instruments, but those other instruments do not know what they are. I think those are most of the types. And then the next most abundant one is pulsar, and so on and so forth.
Okay, thank you. I also have a question. According to dark matters research, why did you consider the spectrum of dark matter as Gaussian function?
Yes, that's so.
Why it's not like delta function?
Oh, why it's not the delta function? That I think we approximate it from the instrument resolution again. So if the Fermi Lab doesn't have like an infinite energy resolution, right? If you use it to observe something at a specific energy, it's not gonna report like the exact energy that is observed. It would have some spread, like it would have some uncertainty in the reconstruction of the energy. So the actual emission could be a delta function, which is this E gamma here. That's a delta function. But when the lab observes it, the instrument can spread it out and make that delta function become something spreading out. And I don't know, the most convenient functional form that we can think of is just Gaussian, I think. So we can just.
So you check that the highest peak of the Gaussian function is the mass or represent the mass of dark matter particles?
Yes, it's this E gamma here. It's represent half of the mass of the dark matter particle.
Yeah, thank you very much.
Yes.
Is there any other questions from the audience? Okay, so if not, I must say this is a very interesting talk, and we have learned a lot about the research that you are doing and you have done in Thailand. It's really interesting, and there are many students have contribution in this research. So at the end, I would like to thanks to Dr. Warit Mitthumsiri, and we can unmute the microphone and then give him applause. Thanks to him.
All right,
thank you very much.
Yes, thank you for inviting me too. It's my pleasure. Thank you for inviting me here.
Okay, then I think next time for the public talk will be Wednesday next week by Iago Escasiba from Autónoma de Madrid in Spain. He will give a talk about the origin of cosmic ray. If you are interested, you can join our public talk next week as well. Okay, then finally, I would like to thank everyone who joined this talk and a nice discussion, and hope you have a good evening and see you next time. Thank you. Bye-bye. Thank you, Warit.
Bye-bye.
Bye.
Thank you. Thank you.